In video 6, we're going to think a little bit more about numerical data, and we're still in this category of descriptive analytics where we're just trying to get a picture of what's going on, but we're going to do a little bit more than what we did in the previous video where we thought about just summary statistics like means and medians. Means and medians and standard deviations and the like are very good for where the data is centered, the shape and the spread or dispersion of data, but we want sometimes a bit more of a picture of how the data is distributed around these central values or the shape, etc. So one way we do that is by producing what's called a frequency distribution, which is just a table of all of the possible kind of values usually put in categories like this, and then how many fall in this category. So this thing here says that there's 1,116 people who earned less than $10,000, and another 939 people earned between 10 and 20,000, and so on. So that you can see straight away gives you a picture which is of some interest in that you can sort of see most of the numbers actually declining as you go down. So the majority of people earn not very much, and then the incomes decline steadily over that. The last category of more than 100,000 is quite big, but don't forget that that covers not just people between 100 and 110, but any amount above 100,000. So sometimes you get a little spike in that last category because it's an open-ended category. So that's what's called a frequency distribution or a frequency table. Usually better presented, or in addition, well, good if you can present it visually with what's called a histogram, and this is a histogram for the same set of data, and so it has that message quite clearly that as the income range categories go up, the number of people earning incomes in those categories declines. The most common category is indeed 100,000. Less than $10,000, and then there's a little spike at the end here for people who are earning 100 or so thousand more. Okay, so that's kind of a visual way, and that's called a histogram. Now, we're going to gradually, through the course of this particular video, shift our thinking a little bit. And so the first step of that is to, rather than sort of looking at these numbers, it's generally speaking better if you actually present things in percentage terms. If I said to you, 759 people earned between $20,000 and $30,000, you'd say, well, so what? What does that mean? But if instead of that I said about 16% of people earn between 20 and 30,000, then you've got a bit more of a feel for it. So obviously percentages generally are an easier way to communicate the ideas. And once again, 23%, if I said 23% of people in the US earn less than $10,000 a year, then you say, wow, okay, I know exactly what you mean by that. Or only 3% of people earn, or just over 3% of people earn more than 100,000. Similarly, that's a number that you can kind of get your head around quite easily. Now, to calculate those percentages is easy. You just have to sum these numbers and divide each of them by the total and turn that into a percentage by how you format your cells. Okay, so first step of making this frequency distribution look a bit better is to refer to it in percentage terms. Now, actually, that takes us naturally to the next step, which is that if we wanted to, we could think about these frequencies in this frequency distribution here as a little bit like a probability table. And so when we talk about 23% of people earning less than 10,000, essentially that means if I came along and randomly picked one of the people from this big data set, just randomly pick one of their names out of the hat and ask what their income was, there'd be a 23% chance that I'd find someone, or 23.79% chance, I'd find someone with an income of less than 10,000. There'd be a 2.73% chance that I'd find someone with an income between 70 and 80,000, etc. Okay, so these are actually probabilities. So if we write them as probabilities instead of as percentages, 0.2379, etc., then that says to us, if we randomly select one individual from this particular sample, the chances of that individual earning, in this case, between 30 and 40,000 would be 0.1234. So that is a probability statement, and so this is a probability distribution. Okay, so with numerical data, a natural sort of, I guess, statistical or foundational statistical idea for numerical data is the idea of a probability distribution, and that's kind of how we think about it in its core form. When we do a percentage table like this or a histogram, we're effectively capturing a probability distribution in visual form. Now, there's a couple of things that have to be true about this particular table for this to be a valid probability distribution. And those things are a couple of technical terms which look a bit fancy, but at the end of the day are quite simple. First of all, the list of the table has to be, and the way the numbers are presented, has to be mutually exclusive and exhaustive. So by mutually exclusive, we means you can't be in more than one category. You can't earn between 40 and 50 and between 50 and 60 at the same time. Now, in this case, it's pretty obvious that's the case. Okay, each of these categories are mutually exclusive. It may not be the case if, for example, I said more than 90,000 here, more than 100,000 here. In that case, a person could be in both categories. So that would be not a valid probability distribution. In this case, no problem. Clearly mutually exclusive. You can't be in more than one category. Second one is exhaustive. It has to capture every possible outcome. So once again, that seems to make sense here. No one can earn negative income. So therefore, I guess zero is excluded. But apart from that, so we said that was $0 instead of $1. Then, and because this is open-ended, doesn't matter how much you earn, there's a category you can fall into. If you're earning $1 million, you're still in the last category. So this is exhaustive in that it covers all the possibilities. Now, because of that, if you added up all these probabilities in this column here, you will get a total of 1. Because mutually exclusive and exhaustive means one of these possible outcomes has to happen, and only one of them can happen. So therefore, the sum of all the probabilities will equal 1, because something out of this list of values has to actually occur. So the probability of something happening here is certain, which means it has a probability of 1. Okay, that's why the sum of the probabilities in the distribution always equals 1. Okay, so that's a sort of technical characteristic of these tables that has to apply in order for them to be thought about as a probability distribution. Now, we're going to take ourselves in a little bit of a sort of mental jump here into something called the normal distribution, which you may have come across in previous maths and statistics courses you've learnt. And the normal distribution is a nice smooth curve like these ones down the bottom of the page. It's sometimes referred to as the bell curve because of the shape of the curve is a bit like a bell. And this is just a probability distribution. The way to think about the normal distribution in the context of how we've been talking about it so far is to go back a few pages to this histogram here, which, as you've seen, is just a table of all the possible categories and the frequencies of occurring. And if instead of frequencies we had probabilities up here, that it'd still look the same shape, it's just the axis would look different. What a normal distribution is essentially a variation on a histogram, which is not looking like this histogram, but rather it's a histogram where the shape of the histogram, if I can just, whoops, I better turn my pen on first before I do that. If I've got a histogram that looks something like the following, excuse my terrible drawing. There's my histogram there. You can see it's got a nice symmetric shape. Most probable there, and as you go down on each side, it's sort of got a bell shape similar to this one here. If you can imagine that if I got more detail on my histogram, and instead of my bars being this wide, if I made my bars more and more narrow, so I got more categories, then eventually I would end up with these things starting to get more and more sort of close together, and I'd get a smoother and smoother looking histogram to the point eventually where my histogram maybe would sort of end up looking a little bit like a normal distribution. Excuse my terrible drawing there, you get the idea. Okay, so that is what this thing here is. This is essentially the result of having a histogram. Each of these bars here could be the bars of a histogram. Each of these points here could be the result of having my histogram bars that have been gradually brought smaller and smaller and closer together so that eventually they end up with a smooth curve. If you imagine that right the way through your histogram, that's what's actually going on here. So a normal distribution is a histogram which has got a nice shape to it. It's symmetric, centered on some middle value where it's most likely, and as you get further away from the middle, the mean, you get less and less values that are less and less likely to occur in both the negative and the positive direction. So that's what the normal distribution can be thought about. Now, this is an example of what's called a standard normal distribution because it's got a mean of 0 and a standard deviation or a variance of 1. So the particular values that occur on the x-axis here are defined by the mean and the variance of that normal distribution, centered on 0 and the spread is 1. So you'll see that once you get 2 or 3 standard deviations above the mean, or 2 or 3 standard deviations below 0, the mean, then most of the probability distribution has already been captured. It's very rare that you get values more than 3 standard deviations above or below the mean. So that's kind of the characteristic of a normal distribution. And that, as I say, is the standard normal distribution, but we don't have to have it looking exactly like that. The shape will always be the same, but it could be that the mean is not 0, the mean is 10, in which case the location of this curve is not centered on 0, but it's centered on 10. And the spread doesn't have to be having a variance of 1, it could have a different variance. In this case, I've got a variance of 9, or a standard deviation of 3, square root of 9. So the spread of this, you can see, is much bigger. It goes from 10 up to sort of 30 and nearly 40 before we kind of get into the very unlikely category. So there's a much bigger spread here compared to this one over this side. Now, actually, out of interest, I think you'll find that's a mistake, that this is actually a normal distribution with a standard deviation of 9, not a variance of 9. So that should actually be 9 squared there. And I know that roughly because typically, once you go 2 standard deviations or so above the mean or below the mean, you tend to get most of your probability being about 0. So 2 times 9 is 18. So when I get to 28, I should have a relatively small probability similar to what I've got here above that. And so a standard deviation of 9 is what we've actually got in this graph here. So just cross out that 9 there and put an 81 instead, because this part of it here captures the variance, not the standard deviation. Okay, sorry about that minor typo. Okay, so that's the normal distribution. It's there because often the result of these histograms with lots and lots of data ends up becoming a really nice smooth curve like that, and there's lots of things that you can do with the normal distribution. In particular, you can calculate probabilities in the normal distribution. So once you, for example, you might have the share market returns on every share in the stock exchange, and you might have that for every 5 minutes of activity in the share market. So you've got literally millions and millions of data points, and you might plot those in some kind of histogram, smooth that histogram out, you'll end up with a normal distribution. And then you can calculate probabilities, such as, what's the probability of getting a normal distribution value bigger than 2 or less than -5 or whatever it might be. So that's what we're doing here with this command called normdist. So for a given normal distribution with a certain mean and standard deviation, what's the probability of getting below the particular x value that I enter? So what's the probability of getting a value below 0 in a standard normal distribution? Answer, 0.5. What's the probability of getting a value below 1.96 in a standard normal distribution? Answer, 0.975. So you can work out the chances, therefore, of getting, for example, a set of share market returns below a certain value. That's one way to do normal. You'll get a chance to practice this in some of the tutorial work that you're doing, so don't worry too much if this is a bit obscure, but essentially what we're doing is taking this standard normal distribution and we're answering questions. The first set of questions we're answering is, if you tell me a value of x, I can tell you the probability. That's what normdist does. Norminv answers the opposite question. You give me a probability, what's the value of x that goes along with that? So in this case, if you told me the probability was 5% or something up here, that means it's 95% down here. What's the value of x that corresponds to that? And that's called norminv. So here you give me the probability, the mean and standard deviation, and I give you the x value that corresponds to, or norminv gives you the x value that corresponds to that. So these are the commands in Excel that allow you to calculate things using the normal distribution, which is quite important if you're wanting to then, for example, work out the risk of, losing all your money on the share market. Well, you might want to know, what is the probability of some value happening, and that value could be some sort of trigger value that causes you to sell your shares because it's got to a certain point in the market. Whatever the application might be, you need to be able to look at the interaction between particular values and probabilities of those values occurring, and these are the kinds of tools that you have at your disposal to do that. There's one other distribution we're going to think about, and that's what's known as the, once I get my page to turn, student's t-distribution. So the normal distribution, as I say, evolved out of a histogram which has got a nice symmetric smooth shape about it. Now student's t-distribution, it's called student's t because it's named after a person called Student. It's nothing to do with university students. has a very similar shape to the normal distribution. It's almost identical. And in fact, with a certain parameter, which is called the degrees of freedom, you can barely tell the difference between them once that degrees of freedom gets fairly large. For small degrees of freedom, the differences are a little bit bigger, but still a very similar shape. So really not much to distinguish between them. The t-distribution, student's t-distribution will come up when some of your later study, when you are involved in doing hypothesis testing or confidence intervals, when you're doing some, excuse me, I'll just get rid of that little instruction from Windows. When you're doing some calculations around the mean and you want to do some statistical test or do a confidence interval. In that case, because you're using the standard deviation from a sample, which involves dividing by n minus 1, and if you remember a previous video, we talked about the difference between n minus 1 and n, then that, in a complicated way that I'm not explaining to you at all here, means that when you do calculations around those things, instead of using the normal distribution, use the t-distribution. So that's the context in which you'll come across it. At the moment, all we want you to be able to do is to know that such a distribution exists, and it's a little bit more spread out than the normal distribution, and as a consequence, so you'll see here there's a little more probability in the tail of this distribution. So it actually arises sometimes in finance where, generally speaking, financial markets behave fairly well, but it happens more often than we like that we have a sort of relatively big change in one day, and so you get a more probability of sort of extreme values happening, either extreme growth or extreme decline. So the t-distribution kind of does arise in finance for that reason. If you want to calculate probabilities with the t-distribution, it's exactly like the normal. You want an x value and you want to know a probability, use t-dist. If you've got a probability and you want an x value, you use t-inv. And then there's a different type of t-inv if you're looking at it two-sided as opposed to one-sided. But I wouldn't worry about that just yet. As I say, you'll get to play with that in tutorial work, and then you'll also get the chance to see its application a little bit later in some of the later videos. And that's all we have for you today. Thank you.